I'm here with Tom Ledoux, who's a science teacher. What else do you teach, Tom?
I teach physics and AP physics, and I also teach seminar, which is for freshmen, and I teach the math and science skills. So we do a skills-based course.
Awesome. So Tom's going to give us a little share of how he's teaching some STEM skills to students, particularly using some technology in hybrid remote environments. So I appreciate the time he's given me. I'm going to pass it over to him. Feel free to take the screen over as well, Tom.
Thank you. So what I'm going to show today is a website that I've been using now for 2 years called Pivot Interactives. It's a web-based browser where students can analyze lab situations. So I'll open up to that right now. So we have here the Pivot Interactives website, and basically what my take is on Pivot Interactives is using these for labs and more specifically lab practicals. So last year in January, I presented to the school committee about how I use lab practicals and my reasoning for using lab practicals in science classes because of the tangible result that students see. They get to see whether or not their answer is right or wrong. Now, in this pandemic, I have to reevaluate when I have, say, 10 kids in front of me today, another 10 students at home today, and then 2 to 3 students who are always home. How can I effectively do a lab practical with that going on? So, like I said, I've been using Pivot Interactives now for about 2 years. It used to be called Direct Measurement Videos when it was free. The website has expanded into chemistry and biology. It was started by a physics teacher. So now it's $5 per student. They do get to work in the browser, and you can set up a classroom. So it really is worth the money that we're paying to have students on this website, especially when you see the high quality of videos. So let's start with the video itself. So if we come down here, we see here we have a little video situation here, and I'm just going to hit play. And we see here we have a cart, and the cart has a collision with the surface, and something is ejected, right? So we have a little puck there. Now, what we're going to do is we can use these videos, and this website has a measuring tool. So if we click up here, and it has some ruler features and a timer feature. And what I'm doing is I can make measurements from the video. If we hit play again, if we hit reset, and let's hit play, and we can pause the video and go frame by frame until it reaches that 0 mark right there. And then I can also reset the timer, time equals 0, and now I can time how long it takes that puck to travel 20 centimeters. So we're using direct measurement to solve for the initial speed of the puck. We can also measure how far the puck slides before coming to a rest. Let me reset the timer because I'll also need time for part 3. So it slid about 8 centimeters and the time 0.3125 seconds. No, none of those really match. Let's guess this one right here. Obviously, I would need to be a little more precise in my measurements. So right there, we have a few warm-up questions just to sort of go over what the video is, how the video works. And now, how do we make this a practical? So I come over here to this Google document that I made here. And what we're going to do is we're going to determine what the coefficient of kinetic friction is between 2 surfaces. So the coefficient of kinetic friction is this relationship that exists between 2 surfaces that are sliding over one another. It's basically like, if I were to explain it to a student the first time, I'd say it's the stickiness factor. Very high coefficients of friction is like when you walk on concrete. It's not a very slippery surface. Low coefficients of friction would be when you're walking on ice. Ice is a very slippery surface. It has a very low coefficient of friction. I won't get into any more of it than just that for right now. My students know a little bit more about the coefficient of friction. But what they're going to do is they can select a different speed at which the puck comes in at, 2, 3, or 4. If we go back to the video here, they can select change. Let's go to 4, because that's the biggest difference, and load, and let's hit play. Oops, sorry, I didn't have the share screen on there. Change, I can go to 4 and click load, and now I'll hit play. Notice how it comes in at a much faster speed and it slides much further. Right? So we're changing variables. We're changing initial velocity of the puck, and we're changing how far it slides. So our students are going to do a little investigation, and what they're going to do is they're going to walk through this experiment to determine what the coefficient of kinetic friction is. So you see here, I've set up this is a pretty early lab. So I've set up some pretty scaffolded questions, like sketching where to sketch, what variables can you measure from the video, and then using the measurements, what can you solve for, right? So I'm really highlighting the difference between a measurement variable, and a calculated variable. And then I ask them what they can't measure from the video, and then we get into the problem solving here with 5. So write a Newton's second law equation and use this equation to solve for mu sub k. Then students compare their results with another group, and I ask them, how does the value compare to yours? Why do you think this is so? And then we talk about sources of error. How could we make the experiment better? If we go over here, this is a whiteboard presentation that I made that students will also be making. And this highlights the questions. So I had them sketch a free body diagram. I had them calculate the initial velocity of the puck. Here are some examples of things that students can measure. And here is how they can calculate the acceleration. Notice here how I get negative 1.89 meters per second squared. And on this one, I get negative 1.86 meters per second squared. So I get different values using different methods, right? And that comes back to how accurate are these measurements right here. How accurate is 0.08 meters, 8 centimeters, and how accurate was the timer, 0.2875, right? If you notice, if you remember how close my time was in the initial one, it wasn't 0.28. So there are some errors that we can talk about using a web-based browser. We can still talk about sources of error, even though we're not actually physically doing the experiment. I continue, we go through the other drawings, what they couldn't solve for using the lab, and then we have the conclusion here. So they actually solve for mu. So number 5, so slide 5 here, this is where they would record other group values once they finish, and they would list some sources of error here. We would do these last 2 slides as a big group, right? So all the groups would discuss, they would share their results on 5, and then we would talk about our sources of error. Any questions, Dan? You're muted.
Up. Yeah, I didn't want my beeping in the background to distract anything. No, that's awesome. I really appreciate how you've modified instruction with noticing how the different sources create different types of errors, and using the tool is amazing that you can bring that kind of real life experiment to the classroom, even if a student's working hybrid. What's been the feedback from students on using Pivot Interactives?
It's been positive so far. I mean, obviously, they'd much rather do the labs. They'd much rather be doing the labs, but I think we're in a situation where all these labs can't be done right now, just given the parameters of the classroom. But it seems to be working well. The students are working through the problems. I'm using it with waves right now. Another cool thing about Pivot Interactives is there are some that you can use even as a demonstration. So for example, right now I'm using a Rubens tube video. For those of you who don't know, a Rubens tube is just a copper pipe with a bunch of holes that you flood with propane gas and light, and then you can pump sound through it, and it creates different levels of flames based on the frequency. We don't have that. We don't have that demonstration device in North Reading, but we have this great video that students can analyze of a Rubens tube.
That's awesome. So this is definitely like even giving you things that you didn't have before access to. So, oh, that's awesome. Well, I do appreciate you sharing this. I'm definitely going to share this out pretty widely, let people see how, you're adapting instruction. I know you use this in your regular instruction as well. So I'm guessing also, this is, you've been translating it more for students in remote learning as well, and adjusting and modify your instruction. So I appreciate all you've been doing as well. So thank you today for doing this as well, and taking the time and sharing what you've been working on.
Of course, no problem. Yeah, and yeah, we did use it in remote learning when we studied electricity and magnetism in physics. So they had some great resources there as well. So thanks, Dan.
Awesome. No, thank you.